All right, the point of this video is to walk you through some basic operations for computing speciation diagrams, both alpha diagrams and log C diagrams as a function of pH using the Hydra-Medusa interface. So this is one of two computational methods or software methods that you might use in an analytical chemistry course to compute or speciate more complex natural water samples. And so this is a companion video. There are several Hydra-Medusa videos on the channel for various applications. This is one of the simpler ones. I'll walk you through its operation. This is the interface for the Hydra component of the software, and the Medusa is a separate package that's used for plotting. So Hydra just collects, it's really just an interface that collects all of the log K thermodynamic data related to all of the different elements on the table. And so if you're interested in modeling speciation for a particular species, for this example we'll do the carbonate equilibria, so carbonic acid in equilibrium with water, then we would think about the element that comprises, that uniquely comprises that species. So for carbonate, that's carbon. We'll click carbon, and then you'll see a bunch of different components that are available for carbon. And the difference in these components, how do you know which one to select? Well, this is obvious because carbonate's the first one, so we would just collect that. But for other things, say for aluminum, there's only one. So there's at least one for every element. There may be more than one, and if there are more than one, it's because it's a different oxidation state. And so for CO3 2-, you won't see HCO3-, the bicarbonate ion in here, because that doesn't change the oxidation state of carbon. So you'll only find one representative species for an entire acid-base equilibrium system. When you have unique components, what you're seeing are different redox states or oxidation states of the element you've selected. So for carbonate, we're just going to select CO3 2-. H plus is default because all the log K data is in aqueous solution, so never delete that. For a simple carbonic acid equilibrium alpha diagram, then we just leave it at this. So we just go to File, Save and Exit. That's going to store that data, and that's going to pull up this little save interface. We'll click Save File and make a diagram with Medusa. That's going to prompt us to save. I'll just call this test for now, so save it in a location that you remember. And then that's going to automatically open the companion Medusa software and preload the file you just saved, which really is just a database file that has all of the carbonate data, the thermodynamic data. It's preloaded as the data file. So there's lots of ways to use this, but the simplest way that I'll show you in this video is just to click Run and make a diagram, because that's our goal, is to make an alpha diagram to see the speciation as a function of pH. And so this is the interface. First thing to do is select the type of diagram. So fraction is the same as alpha. You can select, of all the components you select, I only have two selected in the database, then you can select which one you want to model for. So for here, we're just looking at the carbonate equilibrium, and we want to see how it changes as a function of pH. I can change that either by clicking here, or I can click down here under concentration, and I'll say I want to run this from 1 to 14 in pH. And the x-axis I can vary here. I just want the pH to vary in this dimension. Last thing you can change is the ionic strength if you have a reason to do so. We're going to leave this at 0, which means that everything we're computing is in terms of actual concentrations and not in terms of activities. So once you have everything set up the way you want for your alpha diagram, you just click Make the Diagram. That's going to pull up the computed diagram, which in this case looks like this. So you see what the concentration of the carbonate is. That's actually not going to change the alpha diagram at all, depending on what you do here. It will change if you have multiple components, but if you're looking at a simple alpha diagram for one acid-base equilibrium system, which in this case is the carbonic acid system, then it's not going to change anything. And you can see fraction here, so that's the alpha fraction of each of these species. So at low pH, that's intuitive. We have everything in the protonated H2CO3 form. As we move higher in pH, once we hit the pKa 1 for H2CO3, then we have equal parts bicarbonate and carbonic acid. Similarly, as we move higher in pH, we get to pKa 2, and at that intersection, we have equal parts carbonate and bicarbonate. So that's the first step here. This can be really handy, as it will be for alkalinity titrations, to evaluate, well, what's the starting pH in my system? Right? If I'm starting at a pH of, say, 7 or 7.5 in water, you can say, well, actually what I'm going to have in water is predominantly HCO3 with a little bit of H2CO3 with almost 0 concentration of carbonate. And actually, to have appreciable amounts of carbonate in an alkalinity titration, you can see that we would need to have pHs in excess of 8, really in excess of 9 to be consequential. So pretty alkaline waters to have any measurable amount of the carbonate ion in the overall carbonic acid equilibrium for that water. Okay, I'm going to show you how to make a log C diagram. So I just closed out of the alpha diagram. I opened up Medusa. I can go to File, Data File, and Open. Remember, before when we did this straight from Hydra, I just preloaded it. Now you have an example of where I can just load anything I want. So we made a file called test. I'll just click Open, and that's going to prompt the same diagram selection interface that we saw before. But instead of fraction, I might want to choose logarithmic. And that's going to give me log of concentrations of all the different species on this axis as a function of pH. And I can set the total concentration of the component I chose, and that is the cumulative concentration with all the different species adding up to 0.01 at any given moment. That's the mass balance of that system. We're just going to leave it as default for now, but there may be reason you want to change that. But for demonstrating the use of this, we'll just click Make a Diagram, and now we can see we have a plot that looks like this. And so what's happening in this plot? Well, we have a system where we have the actual concentrations rather than the fraction of that concentration. It's still representing the same thing, right? We have at low pHs everything in the protonated H2CO3 form, and then you have the increasing concentration of bicarbonate and the intersection of these at the pKa1, and at pKa2 you have the intersection of bicarbonate and carbonate. In addition, on this plot you see the concentrations, the relative concentrations of hydrogen ions and hydroxide ions, which you see intersect at 7, which is exactly what you'd expect based on the Kw for the autodissociation of water. So where the fraction or alpha diagram represented simply the distribution of the normalized distribution of each of the species, the log C diagram represents the actual concentration of each of these species if you know the overall concentration of one of them. So if you know the overall concentration of carbonate in the system, then you can speciate out and figure out exactly what the individual species concentrations are, which is especially beneficial when you're trying to speciate a natural water sample. Okay, so the last thing is to, if you want to copy this and use this, you just click copy to clipboard, or you can save it as an image bitmap. Either way, that allows you to pop it into things like PowerPoint or Microsoft Word and annotate the diagram as you need.